Hello and welcome to the first in a series of videos where I will be working through the questions to the released items from the Alberta Chemistry 30 November 2018 Diploma. I will work through these items to show you my thoughts and my thought processes as I work through each question. I would encourage you to try the diploma, this practice diploma yourself before you watch the video. You're going to get the most out of it that way, so that you'll have given yourself a chance to have worked through the questions before I show you how to work through the questions. I'll post the link to these released items. They're a PDF that you'll be able to download and print for yourself. And I'm going to break this into 4 parts, one for each unit. So this video, we're going to focus on the questions related to thermochemistry. This is what the cover page for the document that's linked in the description looks like. I'll also put timestamps for each question, so if you're looking for just how to work through a specific question, then you can click on that timestamp. Some of them might be groups of questions because often there's several questions that come from the same prompt. So again, today we're going to be focusing on thermochemistry questions. If you're looking through this booklet, the first thing that you're going to see is that there is a breakdown. There's quite a bit of intro work, but then there's a breakdown of the different questions here. And you should be able to see, oh, my touch screen is not doing what I want it to do. There we go. I can go this way. There's a breakdown of our different questions, and it gives them it assigns them a difficulty. For right here on the side, there's A, R/U, and HMA. Those abbreviations, which are here, R/U is kind of like the lowest cognitive level. That's what it describes that. It's just a straight remembering or understanding of facts from chemistry. A is an application, which most of the questions are. So you'll be given some sort of example and you'll have to apply the knowledge that you know or things from the data booklet. And then the hardest ones, or the ones that are at the highest cognitive level, are these HMA, these higher mental activities. If you've tried this on your own, hopefully you've looked through the key and you can see what you've gotten right and what you've gotten wrong. And if you're not sure why a question's wrong, that's the purpose of this video, so that we can work through the answers to each question. Looking at question 1 here. Which of the following statements makes a valid comparison between photosynthesis and cellular respiration? Photosynthesis is an exothermic process and cellular respiration is an endothermic process. Both photosynthesis and cellular respiration store energy from the sun in the form of glucose. C, the products in the equation for photosynthesis are the reactants in the equation for cellular respiration. And D, the water in the photosynthesis reaction is in a liquid form, while the water in the cellular respiration reaction is in a gaseous form. This question requires you to know background information on the reactions for photosynthesis and cellular respiration. If you know them, then you will see pretty clearly that the answer to this question is C, that the products in the equation for photosynthesis are the reactants in the equation for cellular respiration. But if you don't know them, I'm going to go through the reactions now. So I'll start with the photosynthesis reaction. Our photosynthesis reaction our reactants are 6 moles of carbon dioxide gas react with 6 moles of water in its liquid form to form 1 mole of glucose, C6H12O6, and 6 moles of oxygen. Sometimes you might see this reaction written with the glucose in a solid form. If the glucose, cells are going to be in an aqueous environment, so this little AQ, I'm sorry, my writing's not great on this tablet. Not that my writing is great anyway. There we go. It means aqueous. The state of water, though, in both photosynthesis and cellular respiration is liquid. And that's important if you're using the table for standard molar enthalpies of formation, because water in a gas state has a different molar enthalpy of formation than water in a liquid state. The reaction for cellular respiration you will see that the products in the equation for photosynthesis of glucose and oxygen are the reactants in the equation for cellular respiration, where we start instead with a mole of glucose, which I'll put in the aqueous state again, reacting with 6 moles of oxygen to form 6 moles of carbon dioxide gas and 6 moles of water in the liquid state. If you're turning these into a thermochemical equation, the energy as a piece of these is either a reactant or a product. Photosynthesis requires sunlight energy, so energy will be on our reactant side, meaning that photosynthesis is an endothermic reaction because energy is absorbed in this reaction. Cellular respiration, the purpose of it is for our cells to harness the energy of this reaction between glucose and oxygen into a usable form, and so energy is going to be on our product side, meaning that cellular respiration will be exothermic. So if we look through our options one more time, photosynthesis is an exothermic process and cellular respiration is an endothermic process based on these reactions. We know that that cannot be true. Both photosynthesis and cellular respiration store energy from the sun in the form of glucose. Only photosynthesis does B, so that's not true. And then D, the water in the photosynthesis reaction is in a liquid form, while the water in the cellular respiration reaction is in a gaseous form. That's simply not true. Both of them are in the liquid form. And that's going to be important if you're asked to calculate the molar enthalpy of reaction for cellular respiration or photosynthesis, that you use water in the liquid state. Moving on to our next question, which involves this enthalpy diagram here. Use the following information to answer numerical response number 1. Here's an enthalpy diagram. Here's our potential energy on our y-axis, and here's our reaction progress on our x-axis. Here we have our reactants, here we have our products. We see that the potential energy overall of the chemicals involved increases when we go from the reactants to the products, and then we have these 2 arrows here where we have I going all the way from this baseline where the reactants are to the top of this peak, and then we have double I, or 2, I guess these are Roman numerals, going from where the reactants are to where the products are. Here are the statements that we can see. Statement number 1, the net enthalpy is represented by 1, the Roman numeral 1. The net enthalpy is represented by Roman numeral 2. 3, the activation energy has a positive value. 4, the activation energy has a negative value. 5, the net enthalpy has a positive value. 6, the net enthalpy has a negative value. The statements that apply to the forward reaction represented by the enthalpy diagram above are numbered blank, blank, and blank. Okay, looking at this diagram, we're looking at the forward reaction. So as we go from these reactants to the products. This numerical response has several statements that are mutually exclusive. Each pair of statements is mutually exclusive. What I mean by that is that both 1 and 2 cannot be true at the same time. I'll pair those up. Both 3 and 4 cannot be true at the same time, and both 5 and 6 cannot be true at the same time. That allows us to narrow down our options because we're going to have to pick a number between 1 and 2, 3 and 4, and 5 and 6 as we work through this. The net enthalpy is represented by either the Roman numeral 1 or the Roman numeral 2. The net enthalpy of a reaction is always going to be the difference in potential energy between the products and the reactants. So number 2 here, Roman numeral 2, this is our net enthalpy. This is our delta H. So 2 is one of the statements that we're going to grab. The activation energy has a positive value or the activation energy has a negative value. The activation energy is always going to have a positive value. You have to input some energy in order to set the reactants in the right orientation with the right amount of energy in order for a reaction to occur. Even if this reaction diagram represented an exothermic reaction, this one's an endothermic reaction, we would still have a positive value for activation energy. Because going from here up to the top of this peak represents our activation energy. So I here, or Roman numeral 1, I keep calling it I, this is our activation energy. It's got a positive value because you have to climb from where the reactants are on this potential energy diagram up to the peak of this activation energy in order to activate this reaction. So the activation energy has a positive value. The net enthalpy, which refers to 2, we've decided, Roman numeral 2 and this number 2, we're going from where the reactants are to where the products are. The products are higher on the scale of potential energy, which means that we have a positive delta H. The net enthalpy has a positive value. So the statements that are true for this diagram are going to be 2, 3, and 5. It's helpful for these types of numerical response questions to break them down into pairs of mutually exclusive statements, because perhaps you knew that the net enthalpy was represented by 2 and it had a positive value, but you didn't remember about activation energies. You narrow it down to a 50% chance of getting this question correct. Just because you know that it can't be 3 and 4 together. So it's a good strategy for trying to break these questions down. It says in any order, so you could rearrange these numbers, any combination of 2, 3, and 5, and you would get this question correct. Moving on to the next question. This will be used for 3 questions, so we'll refer to this page a few times. Different cells use different enzymes to metabolize glucose, C6H12O6. It's written as aqueous here, like I wrote the cellular respiration formula on the first question. In the absence of oxygen, muscle cells will convert glucose to lactic acid, as represented by the following equation, where glucose through muscle cell enzymes breaks down into lactic acid, and we see energies here on our product side. Yeast cells will convert glucose to ethanol and carbon dioxide, as represented by the following equation, and then again breaking down, and we have our carbon dioxide here and our energy, our enthalpy change. A student dissolves 6.5 grams of glucose into each of 2 identical polystyrene calorimeters containing 100 milliliters of water. She then added muscle cell enzymes to the contents of one calorimeter and yeast cell enzymes to the contents of the other, covered the calorimeters, and monitored the temperature change in each. The calorimeter that would have the greatest change in temperature would be the one containing enzymes from which type of cells, and the manipulated variable in this experiment is what added to the contents of each calorimeter. All right, let's take a look at the experiment here. The student dissolved 6.5 grams of glucose into each of the 2 identical polystyrene calorimeters containing 100 milliliters of water. I'm going to highlight this sentence in blue. This is our constant or controlled experimental design. So none of the things here, the mass of the glucose or the type of container or the amount of water, is manipulated. This is controlled. This is the same for each. Then she added the muscle cell enzymes to the contents of one calorimeter and the yeast cell enzymes to the contents of the other. This is what's different. We have muscle cell enzymes in one calorimeter and we have yeast cell enzymes in the other. That is what changes here. The question asked us, well, there's 2 parts. I'm kind of starting with part 2 here because the experiment is most fresh in my mind. We're asking to find the manipulated variable. That's the thing that's different between the contents of the 2 calorimeters. The manipulated variable is the type of enzyme. So I'm going to cross off our 2 columns that say mass of glucose because that's the same. That's a controlled variable. Then it asks me the greatest change in temperature would be the one containing enzymes from what type of cell? Well, let's take a look. If we have the same mass of glucose here, then what changes the temperature most is how much energy is released. We see that we have more energy released from the muscle cell enzymes. We have a larger delta H. I'm going to just draw an arrow here. I'm going to say we have a larger delta H from our muscle cell enzymes compared to the delta H from our yeast cell enzymes. So I'm going to say that the one that has the greatest change in temperature will be the one that has the greatest enthalpy change, or the most energy released by the reaction. So I will cross out our two options where yeast was the option, which leaves us with only one option. Muscle cells have the greatest energy released, and the type of enzyme is our manipulated variable. Again, this sort of question, you can narrow down your results if you know one of the two answers. So it's good. It's helpful to cross them out in these boxes to kind of narrow down your results that way. Going to the next page. In comparison to the reaction pathway without an enzyme, the activation energy for the reaction pathway provided by either enzyme will be what, and the value of delta H for the reaction will be what. You actually don't need to know anything from the prompt box in order to answer this question. You just need to know that an enzyme is a catalyst. And if you look at a potential energy diagram for a thermochemical reaction, you need to know that the only thing that a catalyst does is lower your activation energy. So if you're taking a look at this diagram that I just drew here, where on our y-axis we have our potential energy, and on our reaction pathway and on our x-axis we have our reaction pathway. I guess I don't need to put the delta pH because you can see that it's the change as we move here. This distance here between where our reactants are and the top of this activation energy peak, that is our activation energy, which I'm going to say EA without catalyst, in brackets an enzyme. But if we add an enzyme, we lower the activation energy. This is our EA with a catalyst. In either case, the actual potential energy difference between the reactants and the products down here does not change. So either in the catalyzed or the uncatalyzed reaction, delta H is the same. There's only, one delta H value. So here, if we look back to our question here, the activation energy for the reaction pathway provided by either enzyme will be lower. That's what enzymes or catalysts do. So we'll cross out the ones that say higher. And the value of delta H for the reaction will be unchanged because enzymes and catalysts don't change the enthalpy change. So D is the correct answer. You don't actually need to use anything from the data box on the previous table. Use the following. A student collected the following data during the experiment. This is the mass of glucose. This is the mass of the muscle cell enzymes, the volume of water in the calorimeter, the initial temperature of the calorimeter water, the final temperature of the calorimeter water. Assume the specific heat capacity of the solution is the same as that of water. So having glucose or muscle cell enzymes involved doesn't change the specific heat capacity. So the experimental value for the molar enthalpy of reaction for glucose in this experiment is plus or minus how many kilojoules per mole. This is a calorimetry calculation. All calorimetry calculations are based on the idea of conservation of energy, where your change in kinetic energy, which I'm going to put here in red, your change in kinetic energy is equal to the negative change in potential energy, or negative delta H. If you break down these formulas further, kinetic energy is mass times specific heat capacity times change in temperature, And the change in potential energy is going to be the number of moles times the molar enthalpy of reaction. The little r should go there. Delta RH. What we can use for this reaction is that we are trying to do the experimental value here. Sorry, one thing I should say before I start calculating things. When you see the word experimental value here, you're not using your data booklet. You're going to be use the information from the table above, not your data booklet. I have the data booklet open on another page here. I'm just going to jump over to the other page. If you go to your table of standard molar enthalpies of formation, you could try and do a Hess's law calculation for the molar enthalpy of reaction for this glucose. Based on the fact that you can find ethanol in here, and I guess you can't find lactic acid in this table. But if you went about trying to find a molar enthalpy of reaction based on these standard enthalpies of formation, because you're like, okay, I can find glucose in here. Glucose is right here in the table. Let me get my mouse. Yeah, I highlighted it there. You might think, okay, that's how I'm going to go about solving this question. If you see the word experimental, then go based on these experimental results, not from the data booklet. Going back here to our formula, we are trying to find this, our molar enthalpy of reaction. This is our desired thing here. If you don't remember these formulas, you can also do this by unit cancellation. I'm going to show you both ways here. If you remember the formulas, the formula for our kinetic energy change, this is going to be mc delta T, mass times the specific heat capacity of the thing that's changing temperature times the change of temperature, is going to equal the negative, because whatever potential energy change happens, it's going to be the opposite sign for our kinetic energy. So if our kinetic energy is going up, it means our potential energy is going down. That's what this negative represents. This is the moles of the substance that is reacting here, multiplied by our enthalpy of reaction. This is what we're trying to find out. So if we're trying to find out this, we are going to need to rearrange this formula so we can find that our change in enthalpy, our molar enthalpy of reaction equals our kinetic energy, mc delta T, divided by our number of moles, with a negative sign so that we can get our overall enthalpy of reaction. Though, truthfully, they tell us plus minus here, so it's not going to matter, but it's good to know whether or not it's going to be negative or positive. We can substitute into this equation what we know. We know that our, I will do this, we'll go across this way. We know that our mass of our water, that's the thing that's changing temperature, it's 100 milliliters. Every milliliter of water is 1 gram. So we have 100.0 grams of water. That's our mass. Our specific heat capacity, which you can find in your data booklet, is 4.19 joules per gram degree Celsius. We're going to get our answer in kilojoules. So you can also do this in kilojoules per kilogram degrees Celsius, but I'll do that conversion to kilojoules at the end here because I've just put this in grams already. Our change in temperature is 31.5 degrees Celsius minus 21.4 degrees Celsius. So we have changed temperature by 10.1 degrees Celsius. And we're dividing it by how many moles of glucose we have. We don't actually have our moles of glucose yet. What we do have, though, is our mass of glucose, which is 6.50 grams of glucose, divided by our molar mass of glucose, which is 180.18 grams per mole. I did that calculation earlier, but if you do that to find our molar mass of glucose, it's going to be 6 times 12.01 grams per mole. That's for our carbon, plus 12 times 1.01 grams per mole for our hydrogen, plus 6 times 16.00 grams per mole for our oxygen, which all in total will get us 180.18 grams per mole is our molar mass of glucose. You might want to do this in 2 steps if you are worried about typing it into your calculator correctly. You might want to try and calculate moles first. If you do this calculation for moles first on the bottom of this expression, this is going to be 0.03608 moles of glucose. Then you can multiply this calculation together, divide by your moles of glucose, and you're going to end up with delta RH of negative 117,000 joules per mole. They're asking for it in kilojoules per mole. So we are going to divide by 1,000 to go to negative 117 kilojoules per mole. I've rounded this answer to 3 significant digits already. I know that I have 3 significant digits because my temperature measurement has 3 significant digits as well as my mass measurement. So I've already rounded this. Try typing it into your calculator. You should get something around this as your answer here. I'm not going to show you the unit cancellation for this particular question. I will show a unit cancellation for another question just to show you another way of doing it, but I've kind of run out of space in this area here. This is one way of going about this where you have the formulas. I've written all the units in here. If you're tracking the units through here, you'll see that the grams cancel out between the mass and the specific heat capacity. Degrees Celsius cancels out between the temperature change and the specific heat capacity. And then our grams on the denominator are canceling out between our mass and our molar mass. So what we're left with is joules over moles. And then to convert, we're dividing by 1,000 joules per kilojoule. And then that's going to end up with this kilojoule moving to the numerator. I'm going to do this next page. I'll do this last one. I guess this covers the next 3 questions, and then I'm going to end this video here. So I guess I won't cover all of the thermochemistry ones in one video, but this is kind of post, so you'll know in the video description which questions are covered. Carbon dioxide gas can be captured and used to produce methanoic acid as represented by the following equation. Carbon dioxide plus hydrogen gets us methanoic acid. The methanoic acid, in the presence of a catalyst, can be used to produce electricity, as represented by this following equation. Methanoic acid plus oxygen and a catalyst gets us carbon dioxide and water and 508.6 kilojoules. An enthalpy diagram that could represent equation 2 is which one? Okay. You just need to know, for this particular question, that if our energy coordinate is on the product side, if energy is a product, that means it is released. If energy is released from the system, then delta H is negative. This is an exothermic reaction. Energy is released, delta H is negative. Take a look at these graphs here. We see a drop from the reactants to our products here, and we see an increase from the reactants to the products here. Delta H represents the difference in potential energy between the products and the reactants. If there's an obvious increase, we're starting down here, increasing to here, then delta H here couldn't be negative. That doesn't make sense. In the same way, for D here, we have an obvious decrease, and delta H represents this drop. So delta H could not be positive here. So it's not going to be B, and it's not going to be D, if you remember how these enthalpy diagrams work. This is a kind of testing the same concept as the other enthalpy diagram question, the numerical response. If we look at A and C then, it's going to be one of these two, because this diagram shows a negative delta H and this diagram shows a positive delta H. Then you have to know that if energy is a product, then it's released. So we are releasing energy from this reaction, which means we should see a drop from the reactants to the products. So A is the best representative of this particular reaction. You might also see this written on a test as delta H equals negative 508.6 kilojoules. Instead of saying here delta H is negative, they'll take that actual energy value from the thermochemical equation that they had written above and put it in there. When an enthalpy change of 200 kilojoules is observed in the reaction represented by equation 2, the mass of carbon dioxide that will be produced is what? Okay, I'm going to show you how to do this particular question by unit cancellation. I want to find mass of carbon dioxide. If I'm trying to find mass of carbon dioxide, then I can use something that has grams within its units. Something that has grams within its units is the molar mass of carbon dioxide. So when I'm doing unit cancellation, I'm thinking about what unit do I want. What I want to end up with is grams. And if I don't know which unit I want in a multiple choice question, take a look at the answers. These all have grams. The only thing that I can think of that has grams of carbon dioxide in it is the molar mass of carbon dioxide. Because if I take a look at what's given to me here, nothing in here shows me grams. This is gas state, not grams. So I'm going to start with my molar mass of carbon dioxide. The molar mass of carbon dioxide is 44.01 grams per mole. Each oxygen is 16.00 grams per mole and the carbon is 12.01. So this is 44.01 grams per 1 mole of carbon dioxide. Now I'm going to want to cancel out my moles of carbon dioxide. I want to get rid of moles of carbon dioxide. Well, I can find moles of carbon dioxide from my thermochemical equation. I'm looking at my thermochemical equation here, and I see that in this thermochemical equation, I have 2 moles of carbon dioxide for every 508.6 kilojoules. That's the information I can get from this thermochemical equation. Right now, I have moles of carbon dioxide in the denominator. To cancel out moles of carbon dioxide in the denominator, I'll have to put my 2 moles of carbon dioxide from my thermochemical equation in the numerator, and that's 2 moles of carbon dioxide for every 508.6 kilojoules. This should be a negative 508.6 kilojoules because energy is released from this reaction, so I'll put the negative sign there. Now what I'm left with, this will cancel out my moles of carbon dioxide, is grams per kilojoule. I don't want grams per kilojoule, I just want to know how many kilojoules I have, or how many grams I have. But I can cancel out the kilojoules by what they've told me in the question. The enthalpy change of 500 kilojoules is observed. Well, 2 moles of carbon dioxide produce 508.6 kilojoules, so we could cancel out our kilojoules here by putting negative 200 kilojoules, and that will tell us how many moles of carbon dioxide we have, and then we cancel out our moles of carbon dioxide with our molar mass to figure out how many grams of carbon dioxide we have. And what I'll be left with, if I do 44.01 times 2 divided by 508.6 multiplied by 200, the negatives will cancel out here as well. What I'll be left with is 34.6 grams of carbon dioxide. This next question here will be the last question that I do in this video. Use the following additional information to answer the numerical response question 3. Reaction descriptions. The reaction is endothermic. Reaction is exothermic. During the reaction, energy is released to the surroundings. During the reaction, energy is absorbed from the surroundings. Energy would be a reactant if included in the term in the equation. Energy would be a product if included in a term in the equation. The potential energy of the reactants is greater than the potential energy of the products. The potential energy of the reactants is less than the potential energy of the products. All right. Again, we have a bunch of mutually exclusive statements. If you're reading through these statements, 4 of the statements apply to the reaction being endothermic. If the reaction is endothermic, so I'm going to put these as our blue statements. If the reaction is endothermic, that means that energy is absorbed from the surroundings. If energy is absorbed from the surroundings, then energy would be a reactant. And that means that the potential energy of the reactants is less than the potential energy of the products, because if energy is absorbed, it would have to go into the chemicals. So the products would end up being a higher potential energy. All of those statements group together. The opposite statements, if the reaction is exothermic, then energy would be released to the surroundings. Energy would be a product if it was a term in the equation. And the potential energy of the reactants is greater than the potential energy of the products, just like these potential energy diagrams. Reactants greater than the products because energy is released. This is a classic exothermic enthalpy diagram. We really have 2 options here. Either it's 2, 3, 6, 7, or it's 1, 4, 5, 8. We're looking at equation 1 here. We have to figure out whether or not equation 1 is a exothermic or an endothermic reaction. I'm going to do it by doing Hess's law. So I'll use Hess's law to determine if it's endothermic or if it's exothermic. Hess's law is that delta H equals the sum of our enthalpy change, so moles of our products, multiplied by our enthalpy of formations for our products, minus, I'll switch colors here, the sum of the moles of the reactants, each multiplied by the standard enthalpy of formation of our reactants. So let's write this equation out. We'll just do our equation down here. This is our equation number 1, carbon dioxide gas plus hydrogen gas becomes methanoic acid. I'll change these to blue because I had it in blue above for our Hess's law expression, just to show that our reactants and our products are in different colors. We've only got 1 mole. I'm just going to go back to the other page to make sure I've got that reaction copied down correct. Yep, perfect. All of these standard enthalpies of formation are going to be pulled out of our data booklet here. So you need to find carbon dioxide, which is right there in your data booklet, and we're going to have to find methanoic acid. Methanoic acid is also called formic acid, but it is written in here in the M section. There's our methanoic acid there. Hydrogen is an element, so its standard enthalpy of formation is 0 kilojoules per mole. So if I'm writing out this calculation here, then on my product side, I only have 1 mole of methanoic acid. And each mole of methanoic acid is negative 425.0 kilojoules per mole. That's its standard enthalpy of formation. I took that number right from the data booklet, right there. And then I'm going to subtract the sum of my reactants. For carbon dioxide, I've got 1 mole of CO2, and every mole of CO2 is 393.5 kilojoules per mole, negative 393.5 kilojoules per mole. And I'm going to add our hydrogen. We've got 1 mole of hydrogen gas, but the molar enthalpy of formation for hydrogen gas is going to be 0 kilojoules per mole because it's an element. If I add those together and then I do a subtraction, well, I guess 0 plus 393.5, these are multiplied by 1. It's pretty easy. You just get negative 425 kilojoules minus negative 393.5 kilojoules. You'll get that the enthalpy change in this reaction is negative 31.5 kilojoules. Our moles here cancel out, so all we're left with is kilojoules. If we've got a negative, it means it could be added on to the product side, and this is an exothermic reaction. If we take a look again at our statements, the statements that describe an exothermic reaction correctly are statements 2, 3, 6, 7. And that is our answer. There's still some more thermochemistry questions, but I think I'm going to take a break, and I will put in the description which questions we went through, and the next video will have in its title the questions that we're going to go through there.